Okay, so this is section 13.3, day 2. We're still talking about arc length and curvature. We're just going to come up with a better formula. As a matter of fact, what it says down there is a good formula for curvature is given as the magnitude of r prime of t cross r double prime of t divided by the magnitude of r prime of t cubed. And it's a much easier formula, believe it or not, to use. And it is a really good one for curvature. So what I think we're going to do is this specific video, just going to do probably 2 videos. We'll see how it goes. This one we're going to do the proof. We're going to build this formula, and then we'll do some practice problems in the following video. So in this one, we've got a bunch of information we need to recall, and you'll notice that there's a blank page on the next page. I think what I'm going to do, what I've typically done is started the proof on this first page and then continued to the next page. It doesn't really require that much space, so I'm just going to do the entire proof on the second page. But I'm going to put all the information that we need to recall on this first page, and there's a bunch of it. So let's just go ahead and get started. So one of the things, the first thing, is that we need to remember that ds over dt is the same thing as, because that is that's the derivative of arc length with respect to time, is the same thing as the magnitude of r prime of t. Okay, those are the same. The second thing that we need to recall, and there's going to be like 7 up, so leave yourself a little bit of space here, is that the unit tangent vector, or t of t, is defined to be r prime of t, or the derivative, divided by the magnitude of the derivative, which makes it a unit vector, right? Because r prime of t is the tangent vector, but the unit tangent vector, which is t prime of t, I'm going to say t of t, is dividing it by its magnitude, so it gives it a length of 1. Okay, we need the third thing, which is just a flashcard, that a cross b is the same thing as magnitude a, magnitude b, sine of the angle in between. We need the property of cross products that says if I have a cross b plus c, so I've got 2 vectors being added together in parentheses, and I'm going to cross the resultant of those 2 vectors. It's the same thing as distributing the a. So it's a cross b plus a cross c. We'll put that in parentheses so we can just distinguish those a little bit more. Okay, and that was one of our cross product properties. The fifth thing that we need is that if we take any kind of a vector and cross it with itself, doesn't really matter, I'm just using t in this case, but if you take any vector and cross it with itself, you're going to get the 0 vector. And you can try that. We could show it in general. I'm not really going to waste the time, but create any 3-dimensional vector, cross it with itself, you will always get 0. The 0 vector, I should say. The sixth thing that we need is that if I were to take the tangent vector and its derivative, those 2 things will be perpendicular to each other. Or another way to think about that is that t dotted with t prime will equal 0. Just a good check. And then the last thing that we need is we need the standard formula for curvature that we started off with, which was the magnitude of t prime of t divided by the magnitude of r prime of t. And that's what we developed in the first day of this section. Okay, those are all the pieces that we're going to need. I'll try and make sure I highlight that as we go through this proof. So the idea is what we're going to do is we're going to try to build this. We're going to try and build that formula for curvature. Okay, so according to this, I'm going to need a few things. We're going to need r prime of t. We're going to need our double prime of t. We're going to need to be able to figure out its magnitude. And then we're going to have to come up with some way of getting this r prime of t cubed thing on the bottom. So let's start off with, and I am going to kind of go back and forth here. I'm not going to flip back and forth between the pages, but I'm going to go to my second page to start this. Okay, let's start off with the fact that we know that T of t equals r prime of t divided by the magnitude of r prime of t. Okay, and that's that second, that's number 2. Now all I'm going to do is I'm going to solve that for r of t, r prime of t. So I'm just going to multiply both sides by r prime of t. That's all I'm going to do there. So we're going to get that r prime of t is t of t, unit tangent vector, times the magnitude r prime of t. Again, just multiplying both sides by magnitude r prime of t. But we're going to rewrite that. T of t is just the unit tangent vector, but if you remember that the magnitude of r prime of t is the same thing as ds dt. Okay, and that comes from number 1. So that's property, or the first, not property, but that's the first recall that we had to do. That comes from number 1. So magnitude of r prime of t is the same as ds over dt. A couple things to point out here. This, when evaluated at some point t, or at some value t, is going to be a vector. And while ds over dt could be a function, when it's evaluated at a t value, it becomes a scalar. So it is important to remember that ds over dt as itself is a function. It's a function of t, and then you plug in a value of t and you get out a scalar. But the first one, t of t, is a function of t as well, but it's a vector function of t. So when you plug in t, you get out another vector. Okay, so there is our r prime of t. This is what we need, r prime of t. Now we're going to have to develop the r double prime of t. Well, that's really just a second derivative. So if we take the derivative of r prime of t, we are really taking the derivative of this. And remember, both of those are technically functions until they're evaluated, so it's going to be a product rule. Now, normally I would do the product rule. I would say the derivative of the first times the second. I'm just going to reorder that. So I'm going to put the derivative of the first right here, which is just t prime of t, times the second, ds over dt, plus the derivative of the second. Well, the derivative of ds over dt is the second derivative, and that's the notation, times the first. So I wrote it in a slightly different order than the way I'm used to saying it, but that is still the derivative. Remember, product rule, the order really doesn't matter as much. It's the quotient rule where the order matters more. Okay, so now I've got something for r of t, r prime of t. I've got something for r double prime of t. Now I need to cross those. So we need to do r prime of t cross r double prime of t. Well, that's going to be the cross product of this and this. So I'm just going to literally write it out. I'm not going to actually do the cross just yet, but I'm going to write out r prime of t, which is t of t ds over dt, cross with this whole r double prime of t, which is t of t, second derivative, plus t prime of t, first derivative ds dt. And now we're going to go back and say, okay, well, I do have that property. I believe it was the fourth one, yeah, it's a property. But this was the fourth recall that we put up there. So that was the fourth thing, which says that I have the cross product of something cross with a whole bunch of stuff being added together, so I can distribute the cross product throughout. So that's what we're going to do. So I'm going to have T of t ds dt cross with T of t d squared s over dt squared. That's the first one. Plus, now we'll distribute the first thing to cross it with the second one. So we're going to have T of t ds over dt cross with T prime of t ds over dt. Okay, we're getting there. It's not too much longer. Okay, so the nice thing here is in the first parentheses, that first cross product, remember that when you evaluate this stuff, ds dt and the second derivative, d squared s over dt squared, those are going to become scalars. Okay, so those things can actually be pulled out. Kind of harder to show this one, but if you were to pull a scalar out of, let's just kind of do a, like, I don't know, here's I, J, K, and we're going to say, okay, I've got this thing, I'm just going to write A, B, C, D, E, F, but then I'm going to multiply that by a scalar. Maybe that scalar is 3. And then I'm going to cross this with some other one. I did not leave myself nearly enough room, but there's another one, whatever these entries are here, and then that's going to be multiplied by some other scalar, maybe 5. What that means is I can actually take the 3 and the 5 and multiply those together, because remember the cross product technically is a multiplication, but when it comes to vectors, you have to do it as a vector cross as opposed to I think I'm kind of messing that up just a little bit there, because the cross product is what I have in there. So it's like having, oh geez, I don't even know how to best to describe this. Probably would be best just to let you know that I can multiply when I take out the ds dt and the d squared s dt. It's not factoring, so don't think of it as factoring. I'm literally multiplying this times this, and then I'm doing the cross product of t and t. So really what this is going to give us on the outside here is ds over dt times d squared s over dt squared. Probably the easiest way to say this is technically there are 4 things being multiplied together. I've got t of t, ds dt, t of t, and d squared s dt. Since they're all being multiplied together, I can multiply in any order. The only difference is I still have to write this one as a cross product because it's not the same as scalar multiplication. The other 2 pieces are scalars. They can be pulled out to the front and multiplied first. That was probably the best way to say it. And in the second parentheses, I've got 2 ds dt's, so I'm going to pull those out and multiply them together. So ds over dt times itself is ds over dt squared, not to be confused with the d squared s over dt squared, because that's a second derivative. This is the first derivative squared, not the second derivative. And then that's going to leave us with t of t cross t prime of t. Okay, now we're down to the point where we can use it's formula number 5 for this one particular. Right here, I've got a vector cross with itself. A vector cross with itself, using number 5, is 0. So that whole term is 0 times ds over dt times d squared s over dt. It's all 0. Wonderful. That whole thing is gone. Plus, I also have one where I have t of t cross with its derivative. That's going to come into play in the next step. So for right now, we're just going to go ahead and write out ds over dt squared, t of t cross t prime of t. Got my equal signs. All right, so now we've got r prime of t cross r double prime of t equals ds over dt, oops, forgot my squared, squared and that's just a constant of some kind. Now, I do have something that says, okay, well, if I have the cross product of two things, and I need to take the magnitude of those, which is what we're going to do in the next step. So now we're going to do the magnitude. So the magnitude of ds over dt squared, remember that's a scalar, so the magnitude of a scalar is itself. I don't really have to worry about anything with that. It's just going to be ds over dt squared. But the magnitude of a cross, according to, I think this was number 3 now, I'll put this over here in green, this was number 3 that we're going to use, is defined to be the magnitude of the first one times the magnitude of the second one times the sine of the angle in between. So we're going to have the magnitude of t times the magnitude of t prime of t times the sine of the angle in between. Okay, and this stuff is pretty nice. We're almost there. Because the magnitude of a unit vector, by definition, is a unit vector, is a magnitude of 1. Okay, sine of theta, well, theta in this case is 90 degrees. How do I know that theta is 90 degrees? Well, I am taking a tangent vector and its derivative, and by definition, the tangent vector, unit tangent vector, and its derivative are perpendicular to each other. So that is going to come from the 6th thing that we put on there, that t is perpendicular to t prime, which means that theta in this case must be 90 degrees since they're perpendicular. And if theta is 90 degrees, the sine of 90 degrees is 1. So what that's going to reduce us to is ds over dt squared times magnitude of t prime of t, and that's still my cross, magnitude All right, so what I have on the left side is really our numerator. So let's keep that in the numerator. Oops, forgot a magnitude there. So I'm going to solve this current equation for the magnitude of t prime of t. So I'm going to switch sides here. Magnitude of t prime of t. The way to solve that is to divide both sides by ds over dt squared. So what I get now is the magnitude of r prime of t cross r double prime of t divided by ds over dt squared. And you might be thinking, well, how is this working? Well, now if we look back at the very last thing that we said, that the curvature formula is the magnitude of t prime of t divided by the magnitude of r prime of t. Well, that means if I want to make this, that curvature formula, using the 7th thing that I put on there, I'm going to divide both sides. Whoops, go back to blue here. I'm going to divide both sides by the magnitude of r prime of t. So now what we get is magnitude r prime of t cross r double prime of t divided by ds over dt squared times magnitude r prime of t. So dividing both sides of that equation by magnitude r prime of t. And why would I want to do that? Because according to number 7, on the left-hand side, magnitude of t prime of t over magnitude of r prime of t is curvature. And the right side, magnitude r prime of t cross magnitude r double prime of t divided by, if you remember, ds over dt is the magnitude of r prime of t. So what I get there is the magnitude of r prime of t squared times another magnitude of r prime of t which is going to give me the magnitude of r prime of t cubed. This is the development of our formula. All right, we will come back and do some examples.